Okay, this is video number 3. This one has two quite large topics in it, but the two topics are very intertwined and related, so it makes sense to put them all in one video. You know, if you get tired, you can always take a break. You do need out the empirical problems. I would have handed it to you front back. You can probably also find it in the Mayhem module or even in the stats module. So you'll need that, probably your calculator. Also, I have loaded notes. I'm going to put the notes on the whiteboard, so whatever works better for you. If you want to print the notes and follow along, if you want to write it in your own handwriting, in your notebook, whatever works best for you. So last time we talked about standard deviation. Of course, we also talked about mean absolute deviation, but standard deviation is the real thing. The foundation of statistics and all the stuff that we don't even talk about in Math 207 is based on the mean and standard deviation. See, we want to be able to start to describe data points in relation to the data set. Like, for example, maybe we want to make statements like 95% of data is above 20, or we want to say 84% of women are less than 65 inches tall. Or maybe Anne, let's say she's one of our data points, is in the 16th percentile. We want to be able to make statements like that. So the empirical rule, the word empirical in the English language means from experience. Even when we did probability, empirical meant what did we actually collect data on, what did we experience when we were flipping our coin. So from experience, historically, they looked at a lot of data sets that were unimodal and symmetric. From experience, actually looking at patterns in the data sets that were unimodal and symmetric. These are the only data sets we're talking about because that's the only thing that the mean and standard deviation is valid for. They developed the empirical rule. What's really important to understand, though, is since this was just from studying actual data sets, anything in the empirical rule is really approximate. They couldn't get very precise. This is not theoretical statistics that's based in the foundation of calculus. If you take Math 307, you will talk about something called the normal distribution. That's foundation is in calculus. This is much easier. Actually, in the state of Virginia, it's part of the Algebra 1 curriculum. I'm going to erase and we're going to put up what the empirical rule is. Again, it's only good for unimodal and symmetrical distributions. So this says within number of standard deviations from the mean and the approximate percent of the data. Within 1 is 68%, within 2 is 95%, within 3 is 99.7%. Let's make sure we know what this means, within. So for example, let's say I checked a bunch of playlists on your iPhones or whatever, and I graphed all the different minutes that your playlist are, and it looked unimodal and symmetric, and the mean, we'll keep the numbers easy, is 75, standard deviation is 5. So the mean is 75. So within 1 standard deviation means you're going to jump down 1, jump up 1. So I guess 68% of the playlist will play between 70 and 80 minutes. We could jump up and down another standard deviation for a total of 2 standard deviations. Then we would know that 95% of the playlist would play between 65 minutes and 85 minutes. You could do it again for the 99.7. The thing is, this looks pretty skimpy and short. Because of the symmetry, we can do so much more. So we're going to erase this. I'm going to write something up really nice and big and neat. You're going to want to memorize this because once we create it once, you don't want to have to always start from scratch and create it every single time we have a word problem. So we need a nice big unimodal and symmetrical curve. The mean is in the middle. It really does not matter if we use sample notation or population notation. I'm going to use sample notation. Give me 3 lines on the right, 3 lines on the left. I have not put these in the exact appropriate places. I've actually just put the lines where I have room to label stuff. So this is not necessarily to scale. But this line, we're going to call it plus 1s. 1 standard deviation above the mean. This line is plus 2s. This line is plus 3s. Now if I'm going lower, this is minus 1s. 1 standard deviation below the mean, minus 2s, minus 3s. If we were doing our playlist from just a minute ago, what were my numbers? This would have been 75, 80, 85, 70, 65. Please make sure you know this label is for the boundary. It is not for the space in between. It's for the boundary, for the fence. Now, the empirical rule says, and this is symmetrical across the middle, right? The empirical rule says 68% of the data falls in here. But this area is the same as this area, so I can cut it in half. So I now know that there's 34% there and 34% there. Back to our playlist, then between 75 minutes and 80 minutes, 34% of the playlist. This whole thing is in percent, so I don't have to keep writing the percent sign. Look at the next entry. The empirical rule says 95% is within 2 standard deviations, so between my fingers here, right? I've already filled in 68%. 95 minus 68 is 27% where both of my hands are. Half of 27% is 13.5%. Okay, let's do that one more time. The empirical rule says 99.7% is in between those boundaries, right? I've already filled in 95. That leaves 4.7% for both of those areas together. Cut that in half. This is 2.35%. 2.35. Unfortunately, some internet sites and also some Algebra 1 books stop there. And this really is doing a disservice to our students. Very often when we're doing our word problems, we might just like when we were doing probability, we did the complement rule, we took things away from 1 or 100%. We might want to do that here, but you don't have all 100% filled in. So we absolutely want to fill in these two tails. This was 99.7. You have 0.3% left divided by 2. It's such a little number, I'm going to go ahead and label it up here. 0.15%. You've got to make sure you have that percent sign, right? It's very small. Now I have all 100% filled in. My problems, the word problems we're going to get to in just a minute, are harder than anything you will find in the book because I always want to encourage understanding of the word percentile, particularly as future teachers. You might need to talk with the parents of your students about particular standardized test results and things like that. See, these problems are pretty easy if they give you the mean and standard deviation, because you could just fill that stuff in right away. My word problems are not going to give you the standard deviation. They're going to give you some percentile information. From that, you're going to be able to figure out what the standard deviation is. So let's talk about that for a minute. For example, this boundary right here, what percentile is that? Remember, percentile is the percent of people who did worse than me. So what percent are below me? 0.15 plus 2.35 plus 13.5 is 16%. This is the 16th percentile. Make sure you know that ILE at the end is very important. Let's just do one more. This guy, how much is below? You could start adding up. Hopefully you could start here because you know that's 50, right? And 50 plus 34 plus 13.5. You could think about it as if 2.5% are above me, then 97.5% is below me. That is the 97.5th percentile. The good news is there are only 6 percentiles I can even talk about in my word problems. So you'll see the same 6 come up over and over. You'll probably end up memorizing them. You do not have to memorize them as long as you understand the definition. Percent below me. All right, best way to do this is to start into some problems. We're going to do the first one completely together. Then I'm going to ask you to take some time to do number 2. Pause the video and then we'll come back. And then probably the third, well, we'll hold off on the third problem for right now. So let's do the first problem. Does not matter if you know anything about concrete. They tell you it's well approximated by the normal curve. Let me make sure everybody knows that I'm on this handout now. Okay. The mean is 3,000. The 16th percentile is 2,500. So this is the easiest way to do these problems. Most of the work occurs before you ever get to part A. You have to set up the problem. So drop your mean and label it. Okay. Don't worry about the percentile thing yet. Go ahead, put your 3 lines, and then fill in the areas that you have memorized. That is the very next step. Whole thing is in percent. And make sure you know you need to fill this out on your handout, although I think I have an answer key posted somewhere. Okay. Now we're going to read the percentile information. The 16th percentile is 2,500. So you know 2,500 has to be down here somewhere. The problem is it here, here, or here? That's what the percentile information does for you. You got to figure out which, maybe I'll use my pen, which one of these lines has 16% below it. Not that one, not that one. That one has 16% below it. That's how I know that this line is 2,500. Now, I'm going to talk about jumps. It's not the appropriate word. See how this is one jump? One jump is really one standard deviation. And what distance did it cover? 3,000 minus 2,500. I'm kind of overkilling this, so you'll make sure you understand the process. So one standard deviation is 500. Now, completely overkilling this. Divide both sides by 1. I know I don't have to do that, but now I know that S, the standard deviation, is 500. The thing is, the next problem isn't going to be a 1 there. It's either going to be a 2 or a 3, so you're going to have to divide so you'll know what one standard deviation is worth. I'm sure all of you could have visualized, oh yeah, I'm counting by 500. I want to make sure you know, though, that that is the standard deviation. So let's go ahead and fill in the rest of our lines. So this is everything you need before you start answering the questions. Some of the questions now are very quick because they're visual. What percent are between 2,500 and 3,500? Right? What percent are in between those two? 68. What percent are between 2,000 and 2,500? In between these two, right? 2,000 and 2,500? 13.5. If I ever think you're going to misread a question, I try to underline, bold, all caps. What percentage are outside the interval from 2,000 to 4,000? So we didn't say inside, but outside. So you have this amount and you have this amount, right? Outside. So you got 2.5 there plus 2.5 there, which is a total of 5%. This one says, what is the 99.85th percentile? If you want to pause me for 30 seconds and think about that. All right, the 99.85th percentile. You, of course, can start adding up until you get to 99.85. Might be easier to think about it, though. If I have 99.85 below me, then that means I have 0.15 above me. There's that 0.15 above me. This line right here is going to have 99.85 below it, 0.15 above it. It is E and F that many of you are going to struggle on. Throughout these couple of problems, I'm going to attempt to say it in a few different ways. That is the beauty of a video. If I say too much, you can always back up, rewind, and listen again. Take 30 seconds to see if you can do part E. What percentage of specimens will be at least 4,500? There's that word at least. We had that come up in probability. At least means that number or greater. 4,500 or greater or bigger. So that's just remembering what the word at least means. It's really part F. Now, my position is part F is the exact same concept as part E, except I reversed the way I said it. So let me stay with part E for a second. The question was, what percentage of specimens, will be at least 4,500? And our answer was 0.15%. So I could make this statement, 0.15% of specimens will be at least 4,500. I could just reverse that, right? So part F says 84% of specimens are at least what? What is the answer? 84% of specimens are at least what? You have to find which one of these boundaries has 84% above it. If you want to pause, see if you can do it. Normally in the classroom, when I do this, I find at least 30 to 50% of people have this wrong. The answer is not. That is not the answer. That is 84% less. That's not what the question asked. The question asked 84% bigger. So if I need 84% bigger, then I really need 16% less. The answer is 2,500. Let me say that again. I'm trying to find the line that has 84% at least, which means 84% bigger, which in other words means 16% less. Here's 16% less. Something that's not on these notes, but I feel like I want to do it right now before we go to question number 2. I find that sometimes it's not knowing the definitions in the English language and how they relate to mathematics. So, now, I am giving you some synonyms that are only valid for the empirical rule. These are not mathematical truths. This does not hold for our probability chapter or our algebra section, just for the empirical rule. Percentile, we've already talked about that. That means less than. Other words that mean that, at most, no more than. Those all mean the same thing. If you don't like one word in the bubble, pick another one. Again, just for empirical, I know that this is less than and this is less than or equal to, but on the empirical rule, it does not matter. Then we have the word at least, which means more than, greater than. I think those are the 3 common ways of saying that. Now these are synonym bubbles, which means these words are opposites of each other. And we just practiced that. 84% at least is the same thing as 16% less. Or 84% at least is actually the 16th percentile. So you can, if you don't like a word over here, as long as you do the complement basically, you can use a word here. This is the part that gets the most confusing on the empirical rule. So for number 2, I'd like y'all to take a few minutes, see if you can set up your curve before you start ever doing A, B, and C. Of course, you can always restart the video whenever you want. If you need to get a little help, then you can pause it again to, kind of get you jump started. So that's what is sort of on you as to how you're going to be the best learner, of how often you pause the video. When you come back, maybe just to get a hint, then pause it again. Because again, you want to practice as much as possible. This is a topic that I walk around the classroom. I give students 5 and 10 minutes to work together. Kind of hard to recreate that in an online class in an efficient way. So work on number 2 now. All right. Let's make sure you had your curve set up properly and you got the correct standard deviation. The mean was 70. I'm going from memorizing these. Then it said the 99.85th percentile. That's how you have to know where that percentile is. 99.85 less than me is 0.15 above me. So that is 94. 1, 2, 3. 3 standard deviations equals a distance of 24. So 3s equals 24. Divide by 3. Your s should be 8. So now you know what you're counting by. 78, 86, 62, 54, 46. So at that point, part A should be fairly easy. It's just checking to make sure you set up your curve right. So if you needed help there and you're okay now, pause me again, then come back. Part B, 16% are at least. I need to find the boundary that has 16% above. It is not down here. It is here at 78. Then 84% are at most. At most means less than. I got to find the boundary that has 84% less than it. I wrote part B and C on purpose. After you've done B and C, you should have a duh moment saying, oh, of course, they're the same answer. Because part B says basically 16% bigger. Part C says 84% less. Yes, that's the same fence. This fence, 78, has 16% bigger, which is the answer to part B, and 84% less, which is the answer to part C. So this should make total sense that part B and C had to be the same answer, that it's not coincidence. Part D, I find that students get this wrong for one of two reasons. They're either rounding, and you don't round in my class, or they just don't go carefully and they end up adding up too much. The answer is 83.85%. Make sure you do not have 84%. 84% is wrong. 62 to 94. Okay. Don't add up that 0.15. All right. Normally in the classroom, I'd have y'all practice 3A and D, and then we come back and do the B and C, but we'll keep going with lecture, and we can have you do number 3 for homework at the end of this video. All right, so we're going to hold off on number 3. While I have this up, I'm just going to point to it as an introduction to the next topic of this video. I'm going to erase some of this. You know, I don't know that you necessarily need to write this. It's up to you. On the generic, let me get red. You know how we called that plus 1s, plus 2s, plus 3s, minus 1s, minus 2s? Well, most books will talk just like I did, but they never really use a vocabulary word until you go to the next chapter or the next section. This is one standard deviation up, the 78. That actually is going to be called a z-score of 1. I'm going to put the z-score stuff up in just a minute. This would be a z-score of 2. This would be a z-score of -1. So those coefficients right there actually are named something. They're named z-scores. Basically, z-scores are measuring how many standard deviations away from the mean. So if you are the mean, of course your z-score is 0. But let's put some formal notes up for that. But see, we've already kind of done z-scores. I just didn't tell you that was the name. And maybe a even better introduction, although of course this works a whole lot better when you guys are in front of me. If you took the SATs and the ACTs, you may have been confused as a senior in high school. Like if you got don't write this, but since I have a whiteboard in front of me, if you got a 1200 on your SAT and on your ACT you got a 24, How did you ever know which one you did better on? Some students went to the college website, and if they could tell they were above average on one and below average on another, that was helpful. But if you are above average on both, you still don't know which one was technically better. Some students Google, and there's something called a concordance chart that gives you some idea, like an ACT of 24, approximately in SAT terms what that would be called, but that's still just an approximate. What you really needed was the percentile information. Most students never knew what their percentile was, but the percentiles are actually calculated from z-scores. So just trying to be able to figure out as a senior in high school which one you did better on is motivation, of course, for the next topic, but also the empirical rule, since they're intertwined. All right, let's get some formal notes up. So these are called z-scores. Z-scores are also called standardized scores. Because how can you compare an SAT that's out of 1600 to an ACT out of 36? They're not out of the same thing. How can we possibly compare apples and oranges? Well, there is a way to standardize it down so it's at the same level, so we then will be able to compare them. I'm going to write a little bit, then I'll read it to you. So we have some definitions, some formulas. Z-score is called a standardized score. It is measuring how large or small a data point is relative to its data set. By formula, it's the data point or the observation minus the mean divided by standard deviation. And you can kind of see how the standard deviation is the ruler, right? Because we're dividing by standard deviation. So it's the number of standard deviations away from the mean that a data point is. This, again, is part of the Algebra 1 curriculum. I'm going to erase this now. You know, it always seems like in America, bigger is better and positive must mean it's a good thing. Well, not necessarily. So, again, if you are dead average, you have a z-score of 0. So that means positive z-scores are over here, and negative z-scores, meaning you're below average, are over here. You're above average, you're over there. So when are positive z-scores good? When do you want to be above average? I'll pretend y'all are answering me right now. Salary. If you want to pay me more money to do the same thing, I will happily take your money. Grades. Give me 100. I'll be perfectly happy, right? I kind of know what some of my word problems involve, so let's go sports. Anytime, goals, points, etc. You know, the team with the most points at the end wins the game. Basketball, football, hockey, all of that stuff, right? The bigger, the better. But is there ever a time that you actually want to be below average? Well, you kind of almost pick the opposites. How about debt? Whether that's credit card debt, student loan debt, I'll take my debt to 0. I don't mind. That would be perfectly fine with me. You want to be careful and not say anything like BMI or weight, because this curve is indicating the more and more you get into this tail, the better. At some point, if you don't have enough body fat or weight, you will die. So we want to stay away from things like that. How about, though, risk of cancer? I will be happy to have a 0% risk of cancer, right? And let's go sports. Golf, the person with the lowest score wins. Any timed event, if you ran track, which I definitely did not, but they're not calculating your speed. They're calculating how long it took you to run a certain distance or to swim a certain distance. The person with the lower number, which is the fastest time, wins. So let's just say track or swimming, okay? So as we do our word problems, we're going to calculate z-scores, but you can't just look to see if it's positive or negative. You absolutely have to keep up with the context of the variable. Was the variable minutes to run a race? Was the variable, salary? You have to keep up with what the variable was in the word problem. We have 3 word problems. Part of this, I always try to tell you when I'm very picky on interpretation. I'm going to show you the shortest, sweetest way to say everything that's needed to make a complete interpretation. When you start to ramble, you will probably end up saying something wrong. So we're going to practice correct interpretations. So these are what I call generically z-score word problems. Example 1. Well, let me write it up and then I'll give you a little bit of background. Okay, let's say you took a psych test. You earned a 45. The class average was 38. Standard deviation was 3.5. You took a math test. You earned a 74. The class mean was 65. Standard deviation was 9. And we're trying to figure out which one you're doing better in relative to the rest of the class, right? I do not think this exists at JMU, but it absolutely exists in some of the big famous schools across the country. Think some of the Ivy Leagues, the ones with the weed out programs, whether that's law school, business school, whatever. It's what I call the traditional grading on a curve, that they don't have a syllabus like mine that tells you, oh, if you earn this, you'll get an A or a B. Basically, every student is in direct competition with every other student. The syllabus might say something like the top 30% of students will get an A, the next 10% a B, the next 10% a C, and the bottom 50% fail, something like that. So the only thing that matters is how you rank to everyone else. So let's kind of pretend that that's at play here. So first of all, if you've ever gotten a really bad grade put in front of you in class, I always ask you guys what you do first. Some of you say you cry, and I always tell you that usually that waits until after you leave my classroom, right? Normally what you do is you look around the room to try to get an idea of how other people did. What you're really doing when you do that is you're trying to calculate your own Z-score, how you're doing relative to the class. Let's say you have to call mom up and she said, hey, you had 2 tests. How'd you do? And you're like, well, I got a 45 on psych and I got a 74 on math. Mom's going to start to flip out about your psych test, right? But actually, what's the very next thing you're going to tell your mom? You're going to be like, Mom, I was above average. The mean was 38. I don't know what's going on in that class. And that is actually going to make mom feel better. But we need to get very precise. Let's, again, in my made-up example, you're in Ivy League. You got to figure out which one you're doing better in. So thus, you can figure out which class you need to put your time into studying for the upcoming week or something. The only thing you have to be able to compare two such different classes with different students are Z-scores. So let's calculate the Z-score for psych. Your data point minus the mean over the standard deviation. That turns out to be 2. And for math, your data point minus the mean over the standard deviation. That turns out to be 1. Just so I don't forget what I'm doing, the variable here was grades. So when I see positive 2 and I know it was grades, I know you're doing good. When I see positive 1, I know you're doing good. The only 2 words we're looking for is good and bad, right? So you already knew that. You could already tell you were above average. So that, if you get confused here, you can always look back up and actually just think about the data. So you're doing good. So then which class are you doing better in? So our very specific interpretation is really just 3 different phrasings. I mean, if you want to think back to the empirical rule, you do not have to draw this because I'm going to erase it. I'm going to draw it and erase it really quick. 1, 2, 3. Psych, you're way up here. Math, you're there. And this is the good side for grades. If you want to think about percentile, I guess that's the 84th percentile. 84 plus 13.5, 84. 97.5th percentile. You're doing better in psych than math. But let's again make sure we know exactly and clearly how to word that. Since you did well on both, you did better on psych since psych's Z-score is furthest from 0. So you have to mention whether you did good or bad. Then you have to mention, quote unquote, who the winner is. And then how do you know? It takes all 3. You can't leave out one of this phrasing because then it's not complete. Let me try to point out the places you guys mess this up. We are talking about, this is all about the Z-score. We're talking about the Z-score being furthest from 0 since they both did well. Well, our next example we'll talk about when they're not, or one of the examples is when they both have done poorly. But since you both did well, you want to pick the one furthest from 0, the Z-score furthest from 0. You cannot say since the THE score, because I'm not going to know what score you're talking about. Are you talking about the 45 or the 74? No, we're not talking about those. We're talking about the Z-score. And you can't say furthest from the mean, because I don't know what you mean. Did you mean 38 or 65? No, furthest from 0, okay, because you're deep into the good side. All right. let's do example number 2. This one's calculating the z-scores are not hard, so this one I'm going to tell you the z-score, but then you have to do the interpretation. There's some type of marathon. Let's say Annie competed, her z-score is -2. And let's say John competed, his z-score is -1. And then the question is, who did better relative to the sex? I mean, we want some real life context here. Let's say Annie and John are best friends and they're running the Boston Marathon. Still currently, they do split up genders and then they'll have an overall winner, of course. So, Annie and John want to have just some friendly bet. Maybe the loser buys the pizza that night or something. So Annie is able to figure out how well she did compared to all the females. John can figure out how well he did compared to the males. Now they have to figure out which one did better relative to the sex, because that person's going to be the winner. Oh, sorry, I meant to highlight in a marathon. The negative means you did good. The negative means you did good, because this is not grades. We want negatives on marathon because that means we were below average. Our time was below average, which means we were fast. Get a different color here. So this is another one where they both did well. I just didn't want the negative z-scores to trick you. Since they both did well, Annie did better since her z-score is furthest from 0. So the same interpretation since they both did well. Again, just making sure you weren't tricked by the negatives. Our next problem is when they both do poorly. All right, example 3. I know we're at 48 minutes now. Getting probably a little tiring. This is our last example for this video. Let's say maybe there was some decathlon and these two guys were totally tied until their last event, but their last event are two completely different events. Chris is running the 1500 meter. He runs it in 6 minutes. The mean for everyone else was 4.8 minutes, and the standard deviation was 0.5. Abe was throwing shot put. Throw, discus, shot put, kind of like long jump. He threw it at 65. The mean was 71 with the standard deviation of 5. Excuse me for one moment. Okay, so how do you compare a running event to a throwing event? There's no way, except for z-scores. So z-score for Chris, he threw at 6, everybody else threw at 4, he ran 6 minutes, everyone else 4.8 divided by 0.5. That gave him a positive 2.4, but this was running. So I'm going to go ahead, put in parentheses, because I don't want to forget he did poorly. And you can tell everybody else was done at about the 5-minute mark, and then about a minute later, here comes Chris, right? He was a little slow. Abe. He threw at 65. Everyone else threw at 71 divided by 5. Gives us negative 1.2. But for throwing, that's bad. Because you can tell everyone else threw about 6 feet longer than him. So, again, you can't go with the positives and negatives. You have to keep the context of the variable. So I'm sure we've all watched sporting events where both teams were not playing very well, but there still had to be a winner. Now think about it. If you're, think about your empirical curve. If you're on the bad side and you want to get to the good side, what do you have to go through? You got to go through the z-score of 0. So since they both did poorly, Abe wins since his z-score is closest. Make sure I don't spell closet. Closest to 0. So when they both do poorly, you're picking the z-score closest to 0. Because if I can get back to 0 and then keep going, I'll be on the good side. So that means I'm closest to getting to the good side. All right, let me just kind of give homework or kind of recap where we are. Because I cannot remember if I handed this particular handout out. I know it is still in the stats module, so I don't want anybody to get confused. There is a handout called Experiments, Observations, and Surveys. This is not on your test. We are skipping that. Okay, that saved me a day. So you don't have to do that. Your homework, you should do chapter 30.6. Do the empirical handout, number 3. The answer key is posted in the stats module. Remember, everything is not in the Mayhem module. A lot of resources in the stats module. What else? Oh, I just wanted to point out on page 729 of the book, discussion number 2. It's just a nice example talking about z-scores. You can read from the authors. And this does conclude the new material for the stats tests. So anything we do, whether it's through a WebEx meeting, FaceTime office hours, if I make another video, it's all just going to be review. This is it for the new material, so you should start practicing and re-practicing everything. I'm looking at, I think you'll be fine there. All right, so that is all. See you soon.